In this recording, we will discuss the behavior of capacitors when placed in parallel. Before doing that, we need to make a few precisions. We need to agree on some bits of information. In an electrical circuit, elements or devices are connected by wires. And the other thing that we need to remember is any connected region of wire has the same potential, or any wire is going to have the same potential. Okay, let's go to a simulation that's running here. Let's probably increase the voltage here to have more fun and see some light. Okay, so we have some light here. We'd like to see some light. Okay. Okay, so we have a voltmeter here. So the voltmeter measures the voltage difference between its two probes. So for example, if I place one probe here and one probe here across the battery, it's going to read the voltage across the battery, in this case 67.06 volts. Now, if I place them next to each other, it should read 0 because they are at the same electrical potential. What that statement was saying that we were mentioning, if we have just a wire and no element in between, the voltage is going to be the same. So I should read 0 as long as I remain on this wire. And that's what we are reading. As long as we are remaining on the wire, we are reading 0 volts, meaning the voltage at this probe here, where this black probe is the same as the voltage, the electrical potential, where the red probe is. Now, the minute we go across a device or an element, then we have a voltage difference. Now it says it's minus 11.18. Now, so here the probe was reading 0. Here it was reading minus 11.18. The difference between this voltage that we are reading, the minus 11.18, and the 0 is the voltage across that device. In this case, it's a resistor. So if we put the probes across it, that's what we should read, minus 11.18 volts. Now, if I keep on moving this along this wire, I should read the same minus 11.18 volts. The voltage is the same everywhere on a wire. Remember, the electrical potential in a conductor is constant. Now, if I move across a device like this light bulb, then suddenly I'm in a new voltage. In this case, it's minus 16.76. What you need to remember, 11.18 minus 11.18, and I have minus 16.76. The difference between these two should be the voltage across the light bulb. Now, if I place voltmeter, 5.59 volts, that's the difference between the two. And that's the voltage across the light bulb. And so on. So the idea, let's put this back here. The voltage is constant in a wire. The voltage across a device would be the voltage difference between the wire in one end of the device and the voltage in the other end of the device. The difference between these two electrical potentials is the voltage across that device. That's what this one is saying. The potential difference across an element is the element's voltage. Now, schematically here, if we do this in terms of capacitors, if we start here at 0 volts and we have a capacitor C1, and then we have another capacitor C2, and they are connected by a wire. throughout that wire we are going to have the same voltage. For example, here it's 5 volts. Throughout this blue wire here, they are drawn in the same color just to illustrate the fact that the voltage is the same. We have 0 volts. The voltage across C1 is going to be 5 volts minus 0 volts, so it's going to be 5 volts. Now, the green wire that's connecting capacitor C2 and capacitor C3, it is at the same voltage like it should be. So any point along the green wire is the same voltage, 12 volts, and the voltage across C2 should be 12 volts minus 5 volts, 7 volts. And in here, the blue wire is at the same voltage, same electrical potential, 15 volts. So the voltage across C3 is going to be 15 minus 12, or 3 volts. Okay. Now, how do we connect capacitors in parallel? We connect them in parallel by having a wire that splits into 2 wires, that branches into 2 wires, and such that we have 2 plates connected to each other. And from the other side, the other 2 plates of the capacitor are also connected to each other. Now, since we don't have any device from here to here or from here to here, we can say that the voltage across all that red line is the same. And the voltage across all that blue line is the same. Which means in this case that the voltage across capacitor C1, that's the red electrical potential minus the blue electrical potential, is the same as the voltage across C2, which is the red electrical potential minus the blue electrical potential. So both capacitors are subject to the same voltage, whether we call it V1, V2, or the equivalent voltage. Now, what about the charge? Now, if I have charges coming in to charge the capacitor, some of them are going to come here, some of them are going to come here. That means that both of them together are going to have an amount of charge that's equal to Q1 plus Q2, the sum of charges. Now, to determine the equivalent capacitance, what do we mean by equivalent capacitance? If I have these 2 capacitors, then I would rather use one instead of just the 2. But I would like to be able to get the same charge and the same voltage across it. I would like it to behave the same way in a circle. Now, Q equivalent, Q is CV. C equivalent times V equivalent. So what does that mean? Since V is the same, C equivalent is just Q equivalent over V equivalent, which is just V1 or V2, which is the same. That's what we have here. But if I rewrite this, that's Q1 over V plus Q2 over V. Q1 over V is C1, Q2 over V is C2. So what this is telling me is if I place 2 capacitors in parallel, it's equivalent to having another capacitor whose capacitance is the sum of the capacitance of both capacitors. Okay, that's wonderful. Now, another way of looking at it, if you recall the equation for capacitance, placing 2 capacitors in parallel is very much like adding up the areas. It's very much like this problem that we discussed before, like soldering these two capacitors to each other. So in this case, if I'm going to add the areas, that's equivalent to adding the capacitance, and that's why C equivalent is C1 plus C2. Now, as an example here, we have a 4 microfarad capacitor and a 6 microfarad capacitor that are connected in parallel and charged to 5 volts. We are subjecting them to a 5 volts electrical potential difference. And we are asked to find C equivalent and the charge on each capacitor. C equivalent is just the sum. So 4 plus 6, 4 microfarad plus 6 microfarad, which is 10 microfarad. The charge in each capacitor is just C times V. So for the first one, 4 microfarad times the 5 volts, so it is 20 times 10 to the minus 6 coulombs. For the second one, 6 microfarad times 5 volts, so it's 30 times 10 to the minus 6 coulombs. The overall charge is the sum of both charges, so it's 50 times 10 to the minus 6 coulombs.